Let me start recording. Nice. Okay, let me get started. All right, does the slide look okay?
Yeah, it's fine.
Good. So let me get started. So let me first talk about one thing which I didn't have time to talk about just the photons. And so we talked about this planar polarization, but there should be also circular polarization that appears part of the homework problem. So I need to actually talk about that. So in the case of planar polarization, I expanded the vector potential using this polarization vectors epsilon. And epsilon was written this way for the momentum written in terms of this polar coordinates. So the requirement in the Coulomb gauge was that the divergence of vector potential vanishes. And when you go to momentum space, the divergence, of course, turns into the dotted product between momentum and a polarization vector. So you can easily see that the momentum vector and these two polarization vectors are orthogonal to each other, hence satisfying the Coulomb gauge condition. So this is the way you can expand the vector potential in the momentum modes. And that's what we actually used in discussions when we talked about the decay of the 2p state to 1s state. But as you also know from classical electromagnetism, the planar polarization is not the only basis you can use for the purpose of talking about the electromagnetic wave. And you can also talk about circular polarization. But anyway, so at this stage, we talked about this canonical commutation relations between creation and annihilation operators, and so that the planar polarization states can be regarded as a different species of photons, and only the same species of photons would give you AA dagger of 1, but the different species of the photons will give you the A and A dagger commuting with each other. So that's what we actually talked about already. But the point here is that in addition to this, the basis of the planar polarization, you can also talk about the circular polarization. And I believe you have seen this in the classical electromagnetism. So in the case of the planar polarization, suppose you have the wave going in the z-axis. So in that case, the theta is 0 and phi is also 0. So the momentum vector is 0, 0, 1. And then first planar polarization in that case would be 1, 0, 0. That means the electric field is always in the x direction, and the magnetic field is in y direction. So that's something you can work out. On the other hand, the second planar polarization has 0, 1, 0, which means the electric field in the y direction, and the magnetic field will be in x direction in that case. So the two polarization states will correspond to whether the electric field is in x direction or y direction. So that's the difference between the two. But now in the case of the circular polarization, you take linear combinations between the two so that you consider this linear combination. So epsilon plus will be the combination of epsilon 1 plus I epsilon 2. Epsilon minus would be minus epsilon 1 plus I epsilon 2. And so obviously, because each epsilon 1 and epsilon 2 are orthogonal to the momentum vector, so are epsilon plus and epsilon minus, which are just linear combinations of the two. So this still satisfies the Coulomb gauge condition. And you can also work out the commutation relations between creation and annihilation operator in these spaces, and they satisfy the same commutation relations, namely that if this annihilation operator refers to the polarization plus, and that does not commute with the creation operator for A plus dagger, but it does commute with A minus dagger instead. So the Kronecker delta now is in the basis of plus and minus instead of X and Y. So in this case, the lambda and sigma labels refer to either plus or minus rather than 1 or 2. And correspondingly, the expansion of the vector potential can be now written using this plus and minus. So here you have epsilon plus and epsilon minus together with A plus and A minus. The one thing you do need to be careful though is that now that there's a factor of I in here, and to make sure that vector potential is Hermitian operator or real classically, then this piece, which is the Hermitian conjugate of this term for the annihilation operator, has to come with epsilon complex conjugate, epsilon star. So when epsilon were real, that was the case with the planar polarization, you didn't have to pay attention to this complex conjugation because polarization vector star was the same thing as the polarization vector. But now that you introduce this I here, if you have epsilon plus here, that would be epsilon 1 plus I epsilon 2, then here epsilon plus star would be epsilon 1 minus I epsilon 2 because of the complex conjugation. So you need to pay attention to this star here. But in any case, once you actually use this epsilon 1 plus I epsilon 2, you realize the circular polarization, namely at one instance, polarization may be along the x direction, but it starts to rotate like this, clockwise, and all the way back to x direction eventually, and keeps doing this. Now, at this stage, you can sort of picture this rotation in the clockwise rotation. And of course, I forgot to say that you have to also expand a dot using the same basis. But this basis of polarization sort of circularly polarized, namely that keeps going in a clockwise direction, is an eigenstate of an operator called Helicity. So the photon actually has spin 1, and I'm sure you know this. And when you actually take this dotted product between the spin and the momentum, namely, I'm talking about the quantization axis of the spin of the photon along the momentum direction, then this operator called Helicity has the eigenvalue +1 or -1. So this is very similar to spin 1/2, where the eigenvalue of the SZ projected in a momentum direction can be either 1 plus a +1/2 or -1/2. But because the photon has spin 1, it is actually either +1 or -1. And I also explained on the next slide that when you actually take this inner product between angular momentum and the momentum vector, an orbital piece of the angular momentum is always orthogonal to the momentum because x cross p is always orthogonal to p. So this in this inner product, the orbital momentum, angular momentum will drop out. So you can even replace this s, spin angular momentum, by the total angular momentum, because the total angular momentum would be s plus l. LP started together with P would drop out because that vanishes. So this product would isolate the spin angular momentum once projected along the direction of the momentum. So you could also say that this is the total angular momentum of the photon along the direction of the momentum. So it turns out that this Helicity eigenstate +1 or -1 would correspond to this circular polarization vector epsilon plus and epsilon minus. So that's why this basis of the circular polarization may be more convenient from the purpose of talking about the angular momentum eigenstates and angular momentum conservation. So at this stage, it's just two different bases that would satisfy the Coulomb gauge condition, namely that the polarization vectors have to be orthogonal to the momentum vector. You can either take this real basis for the polarization vectors that will correspond to this kind of the planar polarization, or you can take this the linear combination of the two planar polarization with a factor of I in between, and that will correspond to the circular polarization. And you actually work out the expectation value of the vector potential using this circularly polarized this state, and really see that the polarization vector rotates like this once you actually take the expectation value in the coherent state which corresponds to classical electromagnetic wave. And so you can actually observe this behavior of the electric field explicitly by taking the expectation value of the electric field with the coherent state of the circularly polarized photon. And you can actually work that out. But anyway, so this is just a two different bases you can use for the quantization of the electromagnetic wave. And so that you can find photons also in two different bases, whether you are looking at the planar polarization or circular polarization. So let me stop here to see if you have any questions about this. Don't be shy as usual. No? You sure? Okay, so maybe if we actually go, oh, go ahead. Go ahead.
Yeah. So I'm not sure, because if we have two bases, if we have like planar and then circular, so why don't we just choose one instead of, because the other one is apparently the linear combination of like, so I don't, why bother to have a new one? Because I'm not sure.
So it's basically just the choice of the basis. For example, in the case of spin 1/2, you could have chosen the quantization axis to be along the z-axis, or x-axis, or y-axis, and that's your choice, right? So suppose you use the polarization vector of the circular polarization. So in this case, it's the same thing as choosing the quantization axis along the z direction, and which is the direction of the momentum for now. But when you actually re-express that using the quantization axis along the y, and that's what you do for example spin 1/2, then the spin 1/2 pointing in the y direction is the same thing as spin pointing the x direction, the z direction, plus I times spin pointing downwards along the negative z direction. So that's the same idea that epsilon 1 is now the linear combination of epsilon plus and epsilon minus. So it's the same thing that you can talk about spin 1/2 with a quantization axis along the z-axis, x-axis, y-axis with your choice. In the same way, you can choose these bases of epsilon 1, epsilon 2 that basically corresponds to the quantization axis along the z direction, and epsilon plus epsilon 1 that corresponds to the quantization axis along the z direction. But the quantization axis along the momentum direction actually does have an advantage, because when you actually identify that the quantization axis, the orbital piece of the angular momentum automatically drops out. So then you can say that it's the same quantization axis for the total angular momentum, not just a spin angular momentum. But if you use the planar polarization, then you still have to think about the orbital angular momentum when you consider the angular momentum conservation. So the using helicity basis, namely circular polarization, is more intuitive, but nothing stops you from talking about the planar polarization either. And then people use both for the purpose of, which one is easier to use for the purpose of a particular problem at hand. Does that answer your question?
Yes.
Okay,
Thank
great.
you.
Any other questions? Okay, so the advantage of the helicity basis, the way the angular momentum conservation is more transparent, it becomes obvious once you actually look at this following example. So the first, I just repeat what I said. If you consider angular momentum along the z-axis, assuming that the momentum is also along the z-axis, and then the orbital angular momentum along the direction of the z-axis, namely the momentum direction, automatically drops out because the orbital angular momentum is x cross p. So the orbital angular momentum is orthogonal both to x and p. And then dotted together with the p direction would project the orbital angular momentum along the p direction. But because the orbital angular momentum is orthogonal to p direction, then there's nothing left when you make the projection. So this identically vanishes. So if you consider the total angular momentum along the p direction, and total angular momentum is a sum of orbital angular momentum and the spin angular momentum. But because the orbital angular momentum would drop out when you take the inner product with the momentum vector, the only thing that remains is the spin angular momentum. So when you consider this helicity operator, which is the projection of the total angular momentum along the momentum direction, that would isolate the spin information. So using this, now you can consider the problem, which appears in the homework as well. Suppose you consider the initial state of the 2p atom, where the spin is along the positive z direction. And suppose you also consider the decay of the 2p state to a photon with a positive helicity, namely that this photon has spin along the direction of its momentum. Then you can immediately conclude that the amplitude of this decay will be proportional plus 1 plus cosine theta, where theta is the polar angle of the direction of the momentum of the photon. And the reason is that when theta vanishes, then the spin angular momentum along the momentum direction, which is the same thing as the total angular momentum of the photon, is along the z-axis when theta is 0. Initial state also has the total angular momentum of the atomic state along the z direction. So initial state has jz of 1. Final state has jz also is 1. Then obviously that satisfies angular momentum conservation, and therefore the amplitude is non-zero. On the other hand, when you consider theta going to pi, then initial state has the total angular momentum plus 1 along the z-axis, but final state, when photon is going downwards, would have the spin angular momentum in a negative z direction. But because it's projected along the momentum direction, spin angular momentum in the negative z direction is the same thing as total angular momentum along the negative z direction. Therefore, jz is minus 1. So initial state has jz plus 1, final state has jz minus 1. That would violate angular momentum conservation. And lo and behold, the amplitude in that case will be 1 minus 1 equals to 0. So amplitude vanishes. And when you actually do this integral from the hydrogen atom the wave function and together with the polarization vector, and that is what you're going to find, namely that when the amplitude is computed for the photon going downwards in a negative z direction, the amplitude vanishes proportional to 1 plus cosine theta. So the helicity eigenstates has this well-defined total angular momentum along the z-axis, so that would allow you to understand this angular distribution of the photon direction very easily. So at the end of the day, you take the square of the amplitude and plug that into Fermi's golden rule, and then talk about the probability of the emitting a photon from initial 2p state of the atom decaying to 1s state of the atom. Then you find the angular distribution is given by 1 plus cosine theta squared. And that's the dipole emission. So when you consider the dipole antenna, for example, in classical electromagnetic wave, then you do find formula that goes like 1 plus cosine theta squared or 1 minus cosine theta squared. And then that's exactly reflected in this calculation now in quantum physics. And you see the same behavior of the dipole emission. And when you consider the photon with the opposite helicity state, namely -1, then what the situation is also the opposite. So when the polar angle theta vanishes, initial state of the atom is pointing upwards, so jz is 1. But when theta vanishes, the final state of the photon going the z direction has a spin pointing backwards, namely along the negative z direction. So Jz will be -1. So initial state of Jz plus 1 going to initial state, final state of Jz equals -1 doesn't conserve the angular momentum, so the amplitude vanish. So in that case, the amplitude would be proportional to 1 minus cosine theta, and 1 minus 1 will give you 0, and therefore no probability. On the other hand, when the photon is emitting downwards along the negative z direction, then the angular momentum of the photon going along the negative z direction, but pointing backwards, would be pointing upwards. So the final state photon has Jz of +1, which matches the initial state of the atom of Jz of +1, and therefore the amplitude should be at its maximum. And indeed, 1 minus -1 would be 2. That's the maximum you can have, and that would give you the highest probability. So the probability of the emission of the negative helicity photon would be 1 minus cosine theta squared. And when you consider the total decay rate of the 2p state with angular momentum along the z direction, then you have to add 1 plus cosine theta squared for the positive helicity photon, and 1 minus cosine theta squared for the negative helicity photon. So the total behavior would be 1 plus cosine squared theta. So you have maximum along the z direction, you have maximum along the negative z direction, but you have minimum in the xy plane. And that's the typical behavior for the dipole emission from the dipole antenna. So that's 1 plus what cosine squared theta dependence of the angular dependence is that maximum in z direction, maximum along the negative z direction, minimum along the xy direction. And that's a typical emission you see for the classical electromagnetic wave as well. So the advantage of using this helicity basis or circular polarization is that this kind of angular momentum conservation is very easy to read off. So once you actually do the calculation of the amplitude, and you have to go through this integral of the hydrogen atom wave function. So at the middle of the calculation, it may become a little messy. But if you know ahead of the time what kind of behavior you would expect, then you can proceed with confidence that your integral came out correctly. So that's the advantage of using circular polarization instead of the planar polarization. And that's why I wanted to mention this circular polarization states, which is actually sort of beneficial when you go through somewhat technical calculations, but you have sort of a reassurance that what you're getting is the right behavior because you know this behavior ahead of the time. Okay, let me stop here again to see if there are any questions. Go ahead.
I had a question.
Go ahead.
If the photon is a spin 1 particle, then shouldn't there be a helicity 0 as well?
That's an excellent question. And I was going to actually mention this next. So this is actually something very different from non-relativistic quantum mechanics. So as you saw, the Coulomb gauge condition tells you that the polarization vector has to be orthogonal to the momentum direction. Momentum direction is a vector in x, y, z, the 3 dimensions. So there are only 2 solutions to this. So if the momentum vector is along z direction, then whether you choose the basis of the polarization vector in x direction or y direction, that's the planar polarization, or the circular polarization x plus iy, so x plus iy and x minus iy. So either way, you have 2 linearly independent solutions, but not 3, because it has to be orthogonal to the momentum direction. So there are only 2 possible angular momentum states for the photon. So how can that be consistent with the usual idea that spin 1 would come with 3 states? So when you have S equal 1, you get told in quantum mechanics class that there are 2 S plus 1 states, namely 3. So there seems to be a contradiction between the 2. And the solution to this apparent paradox is that we are no longer talking about non-relativistic quantum mechanics. Photon can never stop. it always goes with the speed of light by definition, because it's light. And so it can never go to the rest frame of the photon. So the idea of this usual counting of number of states in non-relativistic quantum mechanics, that for spin s, you should have 2s plus 1 states, applies when you can go to the rest frame of the particle. If the particle is at rest, then that particle is subject to this angular momentum operator of Jz, Jx, and Jy. You have to satisfy the commutation relation among the angular momentum operators. And for J equals J, then you have to have 2J plus 1 states. And the reason why you have this Jx, Jy, and Jz operators acting in Hilbert space is because none of them would affect the fact that the particle is at rest. So particle at rest, no matter how much you rotate with angular momentum operators, is still particle at rest. So Jx, Jy, Jz operators wouldn't change the momentum vector, which is 0. And that's why you can have all of those, Jx, Jy, Jz, acting in a Hilbert space of particle at rest. But what's different for the photon is that it's always moving in one direction. So let's say the photon is moving along the z direction. Then Jz operator would not change its momentum because that would correspond to axial rotation around the z-axis. So particle traveling along z direction, if you rotate the xy plane, that's the axial rotation around z-axis, is still moving along the z direction, so it doesn't change the momentum of the photon. But Jz operator is good for this purpose, but Jx and Jy are not, because Jx operator would correspond to the momentum, the rotation around the y-axis. So if the particle is moving along z direction, and if you act Jy operator on it, you are rotating the state around the y-axis, which means the momentum going to z direction would rotate to the momentum vector going along the x direction, because rotation around the y-axis is a rotation on xz plane. So what used to be the momentum of the photon along the z direction is no longer along the z direction. You have changed the momentum of the photon. So if we want to keep the momentum of the photon along the z direction, Jy operator cannot be used for that purpose. And same is true with the Jx operator. Namely, if you do the Jx operator, that would rotate the state around the x-axis, which means that would the rotation on the zy plane. So what used to be the photon going the z direction now starts to point along the y direction instead. So Jx operator cannot be used as an operator acting on the state of the photon along the z direction, because that will rotate the momentum vector in off direction. So if you consider the photon going in z direction, then the only angular momentum operator you can talk about is the angular momentum along the z direction that would preserve the momentum going along the z direction. And the angular momentum of the operator Jz is indeed angular momentum operator along the momentum direction on this slide, which would isolate the spin angular momentum along the z direction. So because this only Jz you can talk about, then Jz operator have eigenvalues either +1 or -1, and doesn't necessarily need to have the eigenvalue 0, which you can obtain only when you lower the angular momentum Jz using Jx plus Iy or Jx minus Jiy. And that's the operator you are not allowed to use anymore, because that would end up changing the momentum operator. So you cannot lower Jz equals +1 to Jz equals 0. And hence Jz equals 0 state may not necessarily exist. And as you saw in the quantization of the electromagnetic field, it indeed does not exist. So to put the long story short, when you are talking about the relativistic particles and massless particle like photon, which can never ever stop, it turns out that helicity can take values only for maximum helicity and the minimum helicity, h and minus h, which is s and minus s. For the case of photon, that would be +1 and -1, but not 0. And if you apply the same argument for graviton, that would be the quantum version of the gravitational wave. It has spin 2. And the same argument applies, and it turns out that helicity of the graviton can be only +2 and -2, but nothing in between. When you consider the spin 2 particle at rest, then the angular momentum operator in quantum mechanics will tell you that there should be 2s plus 1, which is 5 states for spin 2, because angular momentum can be 2, 1, 0, -1, -2. So that's a spin 2 states at rest. But for massless spin 2 particle, namely graviton, then angular momentum along the z-axis can be only +2 or -2, but nowhere in between. So that's the same situation as the photon. So essential difference is whether you can go to the rest frame of the particle or not. For massive particle, no matter how small the mass may be, you can always go to the rest frame, and you always find 2s plus 1 states. But for massless particles, like photon and graviton, that's not the case, because you can never ever go to its rest frame. And the spin angular momentum along these the momentum direction, namely helicity, is either +s or -s, but not in between. And you can also talk about hypothetical spin 3½ particles, which appears in a theory of supersymmetric gravity called supergravity. And in that case, then helicity is either 3/2 or -3/2, but never 1/2 or -1/2. Again, s and -s. So that's the essential difference between massless particles, which now you see in quantum field theory for massless particle, namely photon. So this is the initial discussion of the relativity, which we get more and more into from this point on. And this is the first example you see that the helicity operator is only given by s and -s, but not in between, which is different from non-relativistic particle or massive particle, which you can put in the rest frame, where you have full set of 2s plus 1 states. So that's the essential difference between massless, ultra-relativistic particle, and massive particle, which can be non-relativistic and at rest. And you have different number of degrees of freedom between the two cases. Does that answer your question?
Yeah, I think so. That makes sense. Thank you.
All right. Any other questions here? No? Is the explanation of the difference between massive particle and massless particle okay?
Yes.
All right. So then let me finish up this discussion on circular polarization, and then get back to the discussion on the time-independent perturbation theory we started before the break. So let me first review what we have done. So we had this Fermi's golden rule, which we used for the purpose of 2p state of the atom decaying to 1s state by emitting a photon. So in that case, the first order perturbation theory was sufficient for a purpose. So that's why we use this Fermi's golden rule. But there are many cases where we have to go beyond the first order. I mentioned the fact that 2s state cannot decay to 1s state by emitting a 1 photon. You have to emit 2 photons. In this case, you have to go to the second order in perturbation theory. Another example we are going to discuss is the scattering of a photon of an atom, So initial state is that you have atoms sitting and you send in a photon. And the final state is the photon gets scattered in the off direction and an atom still there. So in this case, you also have to go to the second order perturbation theory. So we had to generalize Fermi's golden rule so that we can go to the second order in perturbation theory. So that's the business we started just before the break. And for this purpose, we had to develop this general formulation of the time-dependent perturbation theory. So you can talk about the process where initial state would make a transition to the final state as a function of time, and therefore it's time-dependent perturbation theory. But in its perturbation theory, namely that you should be able to expand your theory in power series in the interaction. And you can have arbitrary order in the expansion, stopping at the first order, that's the Fermi's golden rule we know and love, or go to second order or third order, depending on the nature of the problem, you should be able to expand your theory up to some fixed order in the interaction you are expanding with. So in our case, we are doing electromagnetism, so expansion will be in power series in fine structure constant, or E squared. So you need to be able to expand this transition amplitude going from initial state to final state in power series in E. And when you do the power series expansion in E, and when you take the absolute square to compute the probability, that will be the expansion in E squared, and therefore the fine structure constant. So that's the idea why you have to develop the time-dependent perturbation theory. It's time-dependent because we're talking about transition, and it's perturbation theory because you are doing systematic expansion in power series in E, and hence time-dependent perturbation theory. For this purpose, we went from Schrödinger picture or Heisenberg picture to somewhere in between interaction picture invented by Dirac. So in the Schrödinger picture, all the time dependencies are in states with a full Hamiltonian, and operators don't change the function of time. On the other hand, in the Heisenberg picture, all the time dependencies are in the operators with a full Hamiltonian, but states don't change. Interaction picture is halfway in between. Operators change according to the unperturbed Hamiltonian or zeroth order Hamiltonian, H naught, and states depend on time according to perturbation to the system, which I denoted by V on this slide. So Hamiltonian is H naught plus V. H naught is unperturbed Hamiltonian. V is a perturbation to the system. So V comes with E, if you like. Operators evolve according to H naught. States evolve according to V. That's a separation we try to achieve. But we had to go to a detour because when you just define interaction picture so that the operators evolve according to H naught, time evolution operator of the states was a product of time evolution according to H naught and time evolution according to full Hamiltonian. And naively, if you put the exponents together, then that would be H naught minus H, and that would isolate V. It looks like you have achieved the goal. But because H naught and V may not commute with each other because they are operators, we had to be careful about ordering between the operators. So that's why we had to actually first take the derivative of this operator by T and wrote down the differential equation and integrated it to find the result. And that actually allowed us to do a systematic expansion in power series in V. And we had to go this roundabout way of solving what the time evolution operator is, because you can't simply add the exponents when you have operators which don't commute with each other. So that's why we solve the differential equation starting from this expression with H naught and H in the exponents. We take the T derivative. That actually turns out to isolate V, but together with the H naught still hanging around, And then you integrate the differential operator so that you can find the systematic expansion in power series in V. So that's what we did. Again, you can inject questions anytime you like. This is the review, so I'm kind of going without stopping. But if you have any questions, just please stop me, okay? So what we did is that using this time evolution operator in interaction picture, and time evolution operator, time evolution for the operators in interaction picture, we just went ahead and take the time derivative of them. So time derivative of this time evolution operator for the states in the interaction picture is basically just giving a time derivative hitting either the first unitary operator or second unitary operator. When time derivative hits the first unitary operator, and that would extract h naught from the exponent, that's the first term. When the time derivative hits the second unitary operator, that would extract h from the exponent. You add them together in the middle, and minus h naught plus h is v. So that's indeed what we wanted to achieve. Namely, you wanted to isolate this perturbation, v, from the Hamiltonian. And I insert also the 1 into this expression, namely e to the minus IH naught T over H bar times e to the plus IH naught T over H bar. This is a unitary operator, is an Hermitian conjugate, so the product is just 1. Because in this case, 2H naught are the same operators and therefore they commute. You can add them in exponents, and exponent turns into 0. E to the 0, of course, is 1. So by inserting this combination, I haven't changed anything. But by doing so, I can identify the first 3 operators, e to the IH naught T over H bar, v, e to the minus IH naught T over H bar, which is nothing but a definition of the time evolution of operators in the interaction picture. So operator O at time 0 evolves according to H naught Hamiltonian, unperturbed Hamiltonian, this fashion. And that's exactly the combination we see over here. So we can read off the first 3 operators to be just the perturbation Hamiltonian in the interaction picture, namely Vi of t. On the other hand, the last 2 operators is the operator we started out with, namely the time evolution operator of the states in the interaction picture, namely Ui. So the time derivative of Ui is now given in terms of Vi multiplying Ui. So that's just simply a consequence of taking time derivative of this time evolution operator Ui. So derivative giving something in front is just a differential equation that's easy to solve. Namely, the solution is just exponential of the something in front. And therefore, the solution to this differential equation is just exponential of Vi. But this is the point when we have to be careful about the ordering of Vi's, because Vi is now integrated from time 0 to t in the exponent. And Vi at different times may not commute with each other. For example, in the case of a harmonic oscillator, X operator in an interaction picture would turn into linear combination of X and P, because X and P oscillates in harmonic oscillator back and forth. So at some point, X ends up being purely P, and that surely doesn't commute with X. So Vi at different time would not commute necessarily with each other. So when you write this exponential of Vi integrated at different times, then you have to be careful about the time ordering. And that's why we had to put this big T in front, which corresponds to the time order product. I spent quite a bit of time explaining to you just before the break. And time order product definition is very simple. When you have 2 different operators in the interaction picture at 2 different times, definition of the time order product is always that earlier operators are written on the right and later operators are written on the left. And this is where I emphasize this sort of the reverse time ordering from what we normally write text on a piece of paper. We normally write things from left to right using English alphabets, and that's also true in Chinese and Japanese these days, not in ancient times. Unlike in Arabic and Hebrew, where you write from right to left. And the convention we are using here is sort of like Arabic and Hebrew rather than English and Chinese. You always write from right to left. And that's because of the convention by Dirac of Bra and Ket. So the states are normally discussed using Ket vectors, and Ket vectors have to be on the right. And that's the initial state. An initial state would make a transition to the final state. That's the Bra vector that is written on the left. So that's why initial state is on the right, final state is on the left. So the time ordering has to be done accordingly, namely that starting with the initial state, earlier operators appear first, and then later operators, eventually down to the latest operator on the leftmost, which acts directly on the Bra vector. So hence the time order product follows that convention. Earlier operators are always on the right, later operators are always on the left. So that's the definition of the time order product. So using this definition of the time order product, the definition of this exponentiated operator is really according to this definition in a power series expansion in V. So if you want to stop me, again, don't hesitate to stop me. So definition of this operator in power series expansion in V is the following. So the zeroth order term in V is just 1, and there's no operator, so there's nothing to worry about the time ordering. Also, at the first order in V, you expand this exponent to the first order, which is minus I over h bar with Vi integrated from 0 to t. There's only one operator, so again, you don't need to worry about the time ordering. You do have to worry about the time ordering, however, when you go to the second order in beyond. So at the second order in expansion, you have 1 over 2 factorial and exponent squared. An exponent has minus I over h bar squared, so that's here. But then you have this time integrated operator twice. So you have Vi of T1, Vi of T2, both T1 and T2 integrated from 0 to T. So this integral then is done on the plane of T1 and T2 on a square. But the square have 2 triangles on it. And in the upper triangle, T2 is bigger than T1, and therefore time ordering requires the T2 operator is written on the left, T1 operator on the right. So that's the time ordering. But in the lower triangle, that's the opposite, because T1 is greater than T2 for the lower triangle, and therefore operator of T1 has to be written on the left, operator of T2 has to be written on the right, and that's the definition of the time ordering. So to write this explicitly on this 2-dimensional integral, so this 2-dimensional integral on the square then can be separated into 2 pieces where, the T1 is, I'm not doing this well. So T1 is greater than T2, then it's written on the left. But on the other hand, when T2 is greater than the T1, that's written in the opposite order. But it turns out that that same integral you do on the triangle when you interchange the dummy variables T1 and T2. So you are adding the same thing twice, it turns out. And that cancels this 1 over 2 factorial. So this time ordering can be written now on a triangle instead of a square without a factor of 1 over 2 factorials. So the same argument applies when you go to the third order in the expansion. Then you have an integral over the 3-dimensional space of T1, T2, and T3. So you have a cube, and cube can be divided up into 6 tetrahedra. In each tetrahedra, you have different time orderings between 3 time variables, T1, T2, and T3. And you always order these V1 operators according to the earliest on the right, middle one in the middle, and the latest on the left. So that means for each of the tetrahedra, you always find out the V1 operator for the earliest time on the left, right, the middle time on the middle, and the latest operator on the left. So you are basically adding the 3 operators 6 times according to the time ordering, which appears in 3 factorial and 6 times. So if you divide up this cube into 6 tetrahedra, you can just pick one representative tetrahedron and cancel this factor of 3 factorial, and that actually turns out to be this expression. So instead of writing it in this fashion with the full cube for each order, the hypercube, divided by n factorial, you can always choose one particular type ordering among the operators and integrate only within that hyper tetrahedral, or I don't know how to call this. I think it's called simplex in mathematics. And so you have an integral only for the portion of this hypercube that will cancel one over n factorial. So instead of writing it this way, you can write it this way, integral over the triangle, where T2 goes only from 0 to T1, while T1 goes the full range from 0 to T. That's an integral over the triangle. Or for the 3-dimensional case, this is an integral over one of the tetrahedra. T3 goes only from 0 to T2, so that it is always less than T2. T2 goes from 0 to T1, so that it is always less than T1, but the greater than T3. And T1 goes the full range from 0 to T. And if you do the integral over this tetrahedron, then the time ordering is guaranteed to be T1, T2, and T3 in this order. So instead of adding the same thing 6 times, you can always add one thing once with a specified time order. And this is a more convenient way of computing the matrix element of this time order product in this time-dependent perturbation theory. And once you actually write it this way, you can explicitly verify that this symbolic expansion, we have this the exponential of the time order product, is indeed a solution to the differential equation we wanted to solve. Namely, when you take the time derivative of this time evolution operator, starting with 1 and single integral, to the 2-dimensional integral, 3-dimensional integral, and so on and so forth. And when you do the t derivative, obviously t derivative 1 vanishes. And for the first order term, t derivative would hit this upper edge of the integral. So the t1 is replaced by t, that's this term over here. And when you look at the second order integral, then t derivative would fit the upper edge of the t1 integral. So t1 gets replaced by t. So this argument for the first vi operator becomes t, while the t2 integral still remains. But now that t1 is replaced by t from the upper edge of the integral, this upper edge of the t2 integral becomes t. For the third order piece, t derivative again hits the upper edge of the integral for t1. So t1 gets replaced by t everywhere. So upper edge of the t2 integral now becomes t. T3 integral doesn't change because it doesn't involve t1. And for the operators, I have these 3 operators ordered according to their times. And t1 on the leftmost operator is now replaced by t. But the other operators still have the same arguments of t2 and t3. So the operators are ordered t, t2, and t3, and they are still correctly ordered according to the times because the t is the latest, because that's the upper edge of the integral for t2. Once you write it this way, you can identify that vi of t appears in every single term. So I can factor that out up front. And I can write the rest inside this big square bracket. And for the first term, I factor out minus I of h bar vi. So that gives me 1. For the second term, I factor out this VI and 1 factor minus I of H bar up front. So that will leave still 1 factor minus I of H bar and VI of T2 integral. So that's this one over here. And then I replace this dummy variable integral from T2 to T1 so that this piece looks like the same expression you have in UI. And then you can start to see that this is indeed VI times UI, where VI is the one in front and UI is in this expression down here in the square bracket. You do the same thing for the third order term. You factor out this VI of T up front with 1 factor minus I of H bar. That will leave still 2 factors of minus I of H bar in a square bracket. And I'm left with the integrals of VI of T2 and VI of T3 integrated over this triangle. But once again, because T2 and T3 are dummy variables of the integral, I replace them by Ti and T1 and T2 instead, so that this is now T1 and T2 integral over the triangle. And that expression exactly is the same thing as a second order term in UI. So now you can verify that indeed this expression defined in a time ordered integral does satisfy the differential equation we wanted to solve, namely the time derivative of UI is given by VI times UI. So that's how we verify that this is indeed the correct solution to the time ordered, the time evolution operator. So having written down this time evolution operator in the power series expansion of VI, we want to make sure that the first order piece indeed does reproduce the Fermi's golden rule we used. So we focused on that one. And then use this first order piece sandwiched between the initial state and final state. So that's this one over here. And knowing that VI is a time evolution fixed by the 0th order Hamiltonian, and initial and final states are assumed to be eigenstates of the 0th order Hamiltonian without perturbation. So VI is V sandwiched between e to the minus I H naught T over H bar, acting directly on the initial state ket I, that would extract its eigenvalue EI. On this side, you have e to the plus IH naught T over H bar, acting directly on the bra F. So H naught would extract its eigenvalue EF. So the T dependence is given by this oscillatory factor, given by the frequency of EI minus EF over H bar. Then you can immediately do the time integral because of this simple exponential factor. And so then the probability of the transition would be I initial state going to F final state with a time evolution operator sandwiched in between. You take the absolute square. This matrix element of FVI doesn't depend on time, so that would factor out. I take the absolute squared. Minus I of H bar, absolute squared is 1 over H bar squared. And the time dependencies is only in this integral, you take the absolute square of it. And here we play the trick that you separate this integral into 2 factors because you take absolute squared. One factor, I take the limit that time interval is sent to infinity. And then this integral turns into a delta function, 2 pi H bar times delta function ER minus EF. Once you have this delta function for one of the integrals, and that would allow me to take EI and EF to be the same in the other power of this integral. And then once you insert EI minus EF into the exponent, then exponent vanishes. Therefore, exponential is 1. Integral of 1 is just a time interval t. So this integral absolute squared, one factor is the delta function, the other factor is the time interval. Once you have the overall time interval here for this transition probability, then you divide both sides by t to obtain the probability per time. That's the probability rate or rate of the transition. And that's how you get the rate of the transition, this probability over T, given by this expression, matrix element squared times 2 pi delta function over H bar. So that was the first order of Fermi's golden rule we used already for the 2p to 1s transition. So that's the review. Now we go to the new stuff, namely working out Fermi's golden rule at the second order perturbation. So why don't I stop here now that I finished the review and to see if you have any questions about this?
I have a question
about
the time ordering operator. I know you already went through it, but I would really appreciate if you could just like maybe make the harmonic oscillator example again, and maybe like explain what V of T1 and V of T2 would be in this example. I would really appreciate that.
Right. So if you have the time, some perturbation to the system, and that could change, let's say, the ground state of a harmonic oscillator into an excited state of a harmonic oscillator. So the perturbation you might add to this, maybe let's say you have x to the fourth. And if you have x to the fourth in here, then you would like to compute the transition from x at the ground state I to some of the excited states. And x to the fourth in interaction picture would change x at the initial time to x cosine omega t plus p sine omega t, I think over m omega or something. So x to the fourth in interaction picture would be this x cosine omega t and p sine omega t to raised to the fourth power. So if you expand that out, you have x to the fourth, x cubed p, x squared p squared, xp to the p cubed, and p to the fourth in it. Then you insert that operator in here to compute the matrix element. But you don't need to deal with this funny linear combination of x and p, because all there is that this is the time evolution according to the zeroth order Hamiltonian, namely the half 2m 1 over 2m p squared plus half m omega squared x squared, that's h naught, and h naught directly on the initial state and final state. So that would extract this energy eigenvalues of the initial state and final states according to the harmonic oscillator. So EI is h bar omega times 1/2. EF is h bar omega times n plus 1/2. So EI minus EF will be h bar omega times minus n for the excited state n. Then you actually compute this time integral, and that would turn into delta function and time interval. And so in this case, we are considering this V to be time independent. Therefore, the delta function forces you for EI to be the same as EF, namely that you would never ever have a transition from the ground state to excited state. And that's what you would expect. If the perturbation is time independent, then initial state of energy h bar omega times 1/2 would stay with the same energy of h bar omega 1/2 and doesn't change. But you can still have interesting transition when you consider, for example, the three-dimensional harmonic oscillator. So in this case, when you consider the first excited state, the first excited state may be n along x direction, n along y direction, or n equal 1 along the z direction. So you have three states at the first excited state. And together, they actually form the angular momentum state of L equals 1. Namely, the first excited state has the orbital angular momentum of 1. And when you do the perturbation, according to, let's say, x to the fourth I mentioned, then it might actually change one of the x states into y state or z state, depending on what kind of perturbation you do. So in this case, you can have the transition from one of the p states to one of the other p states, according to the perturbation, without changing the energy, according to time interval t. So then you can compute the transition of the one of the p states making transition to one of the other p states, satisfying energy conservation, And then you can compute the transition rate, namely probability over T, using the perturbation satisfying the energy conservation. So that's one example of using harmonic oscillator for H naught, and consider some perturbation V at the first order in expanded perturbation theory using the first order Fermi's golden rule. Does that answer your question, Alessandro?
Yes, thank you so much.
Okay, good. But if you go to the second order, then you of course see something a little bit more complicated. Any questions at this stage? Okay, I'm not hearing one. So let's just delve into second order perturbation. And the idea is still the same. But because you have now two perturbation Hamiltonian in between, coming from the second order, then I have to insert the complete set of states in between these two V's to compute this matrix element. So by definition, Vi of T1 is given by this first product, e to the IH naught T1 over HV, HV e to the minus IH naught T1 over H bar. So these three factors is the V1 of T1. Vi of T2 is the product of these three operators, e to the IH naught T2 over H bar V e to the minus IH naught T2 over H bar. So that's just writing this out explicitly. And sandwiching that between the initial state I and final state F. This rightmost e to the minus IH naught T2 over H bar acts directly on the initial state I. So that would extract the initial energy EI. This leftmost e to the H naught T1 over H bar would act directly on the bra F. So that would extract the eigenvalue of H naught on bra F, that's EF, the final state energy. But I'm still left with this time evolution operator in between. So we need to somehow work this out. And to work this out, I insert the complete set of states between these two states operators V. So this is the decomposition of unity. You insert that in between. So between this first V and this time evolution operator over here. So I have the sum over intermediate states M over here. And this M has a matrix element directly with the operator V and F. So this part doesn't have any time dependencies, but the rest does. So this M now has this time evolution operator still left from time T2 to T1. And this other perturbation Hamiltonian V is still left, acting directly on the ket I. But now that I have inserted this complete set of states M in here, H naught act directly on this bra M. So that would extract this eigenvalue EM. So this H naught now becomes a number EM. So I can extract that between bra and ket because it's now a number. And that has a time dependence from T2 time to T1 time, T1 minus T2. So now I have this expression. And extracting everything that doesn't depend on time now. So this matrix element doesn't depend on time anymore. This matrix element doesn't depend on time either. And sum over M doesn't either. So I extract all of these factors up front. So I have sum over M. I have this matrix element from M to F, this matrix element from I to M. So the interpretation is very simple. The perturbation would turn the initial state I first into this intermediate state M, and then finally to the final state F in 2 steps instead of 1 step, because it's second order perturbation theory. And all the time dependencies are in these exponential factors that need to integrate it over the triangle on this 2-dimensional T1, T2 space. So from here to there, I'm just following the definition just in a straightforward fashion. Then I need to perform this time integral, just like in the first order case. So I just move this integral up there. And once again, we are interested in the limit where time interval is long. So make the T2 integral into the infinite integral. But we need to actually make sure that these integrals converge. So we play a little trick. So for this time, the integral for T1 and T2, we put in a small exponential damping factors. And this is just meant to be the mathematical trick, but we keep track of this small parameter epsilon for the rest of the calculations. So if epsilon is positive, then even if you send T2 to infinite, then this damps exponentially. So you will guarantee that these integrals would converge. Once you play this trick, then you can perform T2 integral first on this first exponential factor, which oscillates with EI minus EM. T2 integral would bring the inverse of this exponent, that's this denominator, minus EI minus EM. But now that we stick in this mathematical trick of this damping factor epsilon, I need to keep track of this plus I epsilon. Then this upper edge of the integral will be given by this one, evaluated at T1. And then I still need to keep track of this one over here. Then you also perform EI T1 integral of this exponential, and that will lead to the delta function in the end in the limit of the infinite time interval. So that's how you can perform the time integral. But now you have this denominator, which has this I epsilon in it. And this may be the form you have seen in quantum mechanics class. Namely, you have this matrix element for the transition from initial state to intermediate state. You stick in something you call the energy denominator, because the energy difference between the initial state and the intermediate state appears in the denominator. And finally, you make the transition from intermediate state to the final state of your interest. Then that's the second matrix element, and that's the expression you have. And you might wonder why I don't have this exponential factor in the numerator, but because you are sending time interval to infinity in the end, this damping factor would damp this exponential factor to 0. That's why I didn't have to take care of the second exponential at the end of the day. So this is the final expression we need. So at the second order perturbation theory, I have the usual delta function in energy, which you need anyway. And you have the matrix element of going from initial state to intermediate state M. You have the energy denominator, and then from the intermediate state M to the final state F. So that's the result of the transition amplitude at the second order perturbation theory. Okay, let me stop here again to see if we have any questions. Have you seen this in quantum mechanics class? Please say yes or no, at least one of you.
No.
You have not, okay. So this is the first time you see it, so then you should really ask questions about this.
Can you repeat what it means for the energy denominator?
Yeah, so this energy denominator came from integrating this exponential factor as a function of T2 from initial time to T1. So this is exponential. So T2 integral would require you bring this EI minus EM into the denominator, because this denominator times this exponential, if you differentiate with T2, would cancel this EI minus EM in the denominator so that you recover the integrand. So integrating this with respect to T2 would require this exponent to appear in the denominator so that the derivative of this integral would reproduce the original integrand. So that's why we have this CI minus EM in the denominator.
Yeah, I
that good?
understand where it comes from,
Okay.
but
All right.
the thing I don't understand is because now if we have the energy denominator, we have the I epsilon, where if the energy denominator should be all real quantities, then I don't understand, because it's now a combination of real and imaginary parts.
Yeah, so that's an excellent question, and we'll come back and talk about this. So, for example, when you consider the scattering of the photon of an atom, suppose you have a hydrogen atom in 1s state, and you send in a photon whose energy is precisely the energy difference between 1s and 2p states. Then sending energy into atom that can excite the atom to the 2p state. So M is now the 2p state. I is the 1s state and photon. Then the energy EI is the sum of the 1s state plus energy of the photon. EM is the energy of the 2p. And they may exactly equal to each other if you tune the energy of the initial state to be precisely energy difference. Then this energy denominator seems to become infinite unless you have this I epsilon in it. But of course, probability would never be infinite. We are dealing with physics. So what should happen then is that it turns out that this I epsilon would actually receive a correction, which corresponds to actually the lifetime of the 2p state. And because 2p state is unstable, which means that delta t is finite for 2p state, you have energy and time uncertain principle that will make the energy of the 2p state finite, uncertain, namely that dE of the 2p state is h bar over the delta t, which is the lifetime of the 2p state. So energy of the 2p state now becomes a little bit uncertain, which means that EM, energy of the 2p state, ends up acquiring an imaginary part. That would correspond to the decay of the 2p state. And we will talk about this later when we talk about the resonant scattering. Namely, you send in a photon that would resonate to the energy difference between 1s and 2p state. And that does not give you infinite probability because it turns out that what you mean by energy of the 2p state has a little bit of imaginary part in it, so that e to the minus IET would be exponentially damping. So imaginary part of the energy corresponds to the exponential damping of the state. So that it in turn gives you a finite imaginary part to the energy of the EM, which comes with some sign of I epsilon. So you keep I epsilon as a sort of the mnemonic or reminder what sign of imaginary part you're supposed to keep for the energy of the 2p state. And once you actually stick in this imaginary part of the energy of the 2p state at the end of the day, everything is finite. And you do find the finite probability in the end. So we will come back and talk about this. So at this stage, we keep this I epsilon as a way of remembering what is the correct sign of the imaginary part when you stick in the lifetime effect of the energy of the 2p state later on. And so this I epsilon in the end, you don't need, but this is the way of remembering what is the correct sign to make sure that you never see anything exponentially increasing, which you can never achieve by arranging the initial state correctly, but you always see something that exponentially decays. That's sort of the increase of entropy. You can never arrange the fragments of the glass to go back and form a well-defined glass you can hold in your hand. You can only shatter a glass, but you can never build a glass like this one over here, because that's the increase of entropy. You can never create a state that would increasingly produce 2p state exponentially increasing. You can never do that by arranging the initial state, but you can always have the 2p state decaying. And that's the same thing as keeping track of the sign of I epsilon. And once you keep this track of I epsilon in all of these energy denominators, it might look like you're doing something strange on the way, but that will allow you to keep track of the sign when you include the lifetime of the 2p state into the calculation. And that's how everything turns out to be finite in the end. And epsilon is just a reminder for you, which you don't need at the end of the day of the calculation. So this is just a first trick so that you can remember that we can always deal with something that's exponentially decaying, not exponentially increasing. Does that answer your question?
Yes. Then I have one more quick question. Is that
it is K?
Yes,
I don't see the name. Yeah, okay.
Yeah. So now I'm confused because the originally we introduced epsilon because we want the integral to converge. But now it seems to me that it is can I say an intrinsic property of the decay is an intrinsic property that we introduce it. So
right.
I don't know which
so
to begin with.
Yeah, we will come back and talk about this. So please hold on to the question for now, and then we'll come back and talk about this when we get to resonance scattering. That's sorry that I can't answer this question today because of time. But let me just tell you what this energy denominator actually means, and it's meant to be what we call the virtual intermediate state. So we can write these diagrams to understand and keep track of these expressions. So for the first term in first order perturbation theory, the I initial state goes directly to the final state by virtue of this interaction V. So you can draw a diagram like this one, which is called the Feynman diagram. And second order piece can be drawn like this. Initial state I comes in, it interacts, and then becomes the intermediate state M. And whenever you have this intermediate state M, you write what we call the propagator, which is the same thing as energy denominator, just to say the different name for it. And after the state I turns into M, propagates from time t1 to time t2, then hits another interaction and goes into the final state F. That's this last matrix element. So if you draw a diagram like this one, you can immediately translate this diagram to this expression in the amplitude. And that's what is called the Feynman diagrams. And drawing these diagrams are very easy because you just keep drawing arrows from initial state. And each time you hit this interaction, each time you have an intermediate state, you stick in this energy denominator. Each time you hit the interaction, you stick in the matrix element, and you keep doing it. So if you want to draw the diagram for the third order, then you can do it very easily as well by inserting this energy denominator or propagator. So the third order, I hits V, going to the first intermediate state. You have this propagator. Then the second intermediate state, you go to the propagator and then you hit another interaction. Then at that point, you stick in another matrix element going from intermediate state M1 to M2. You stick in another propagator for M2 state, and that would hit interaction, and M2 state would go to the final state F. So that would have matrix element, propagator, matrix element, propagator, matrix element. And you can generalize this to any order in perturbation theory. So once you have this idea of this diagram, you don't need to go back to this time order product business anymore. You just write down matrix element, propagator, matrix element, propagator, and matrix element going to the final state. And that's all you need to remember. And then you know how to write down the amplitude. You take absolute squared and the delta function to compute the transition rate. And now what you do in perturbation theory for our purpose is when you compute, for example, 2s decay to 1s, you use this operator in two different ways. One thing you can use is to use this a squared piece. A contains the product creation operator photon. So this piece stuck into the first order amplitude can generate two photons at once. But you can also use the PA operator twice in a second order perturbation theory. 2s state turns into 2p. This is the intermediate state to 2p. That's the first transition matrix element. Then you can stick in this energy denominator. That's the propagator. And so 2p state propagates from time t1 to t2. And then you have the second matrix element of 2p state going into the final state 1s. And each time you stick in V, which is P dot A contains the creation operator photon. So this transition in matrix element produces one of the photons. And second transition matrix elements produces the second photon. So that will also produce two photons. But this intermediate state doesn't have to be 2p. It can go to 3p and come back. It can go to 4p and come back. And you need to sum over all these intermediate states at the end of the day. So that's how you compute the decay rate of the 2s to 1s, now that you are dealing with a second order perturbation theory. So this is the idea I wanted to communicate with you. And just again, to finish up this class today, the only thing you need to remember at the end of the day is this diagram. So whenever you actually go to some nth order perturbation theory, the only thing you need to do is draw this diagram. Then initial state has this matrix element going to some intermediate state M1. Then you have the propagator for the state M1 with energy denominator. M1 state can make a transition to the next intermediate state M2 with a matrix element of M1 going to M2 with a V in it. And then you have energy denominator for M2 state, and so on and so forth, until you hit the final interaction of Mn state going into final state F with the matrix element, and sum over all intermediate states in between with multiple matrix elements and multiple energy denominators. And that's the nth order piece in the time order perturbation theory. In the end, that's the only thing you need to remember after going through all this algebra of the time order product and time integrals at the intermediate stages. And that is what we call the Feynman diagrams. Okay, so this is the end. Sorry, I went over time. Any questions?
I have a quick question.
Go ahead.
So we regard the energy denominator as a propagator, but if we take the analogy of say a Hamiltonian, which is called to ddt, then it's very likely to be the time evolution. But I don't understand why the propagator is proportional to 1 over e.
So it's basically that we went from the time domain to energy domain or frequency domain. So energy and time are basically sort of Fourier transform to each other. The initial expressions was written explicitly with time. So T1, T2, T3, and so on. So that was ordered in time. So if you follow this as a time ordering, so initial state would hit the first Hamiltonian at time Tn, second Hamiltonian at time Tn minus 1, third Hamiltonian at Tn minus 2, ... in the end to the T2 and T1, and then to the final state. So you're hitting this interaction Hamiltonian n times that way. But by performing the time integrals involved in this expression for the time the evolution operator, then time integral would turn into energy denominator for each of the intermediate states. So instead of doing a time integral at each time slices, once you go to the energy domain, that's the same thing as inserting this propagator for each of the intermediate stages. Does that answer your question?
Yes, thank you.
Okay, good. Any other questions?
Sorry, about the Fourier transformation. I think it looks like when we first introduced the epsilon, the damping factor here, it's like we're doing a Laplacian transformation, right?
Right, that's right, sort of. Yeah, so time is slightly rotated, yes, in the imaginary direction.
Okay, and does the Laplacian transformation plays a special role in quantum field theory, just like the Fourier transformation, because we know that the position and momentum, they're just essentially a pair of Fourier transformation. Does the Laplacian transformation play something like this?
Yeah, so going from this Fourier transformation with I epsilon would allow you to rotate the time axis now to the imaginary time direction. And then it becomes a Laplace transformation instead of the Fourier transformation. So as far as the integral is concerned, as long as you can rotate without hitting a singularity, then the answer doesn't depend on which way you do the integral. So in the end, the Fourier transform turns out the same thing as Laplace transform. But then you have an expression written as an integral along the imaginary time direction. And that is indeed called imaginary time formulation. So in many of the calculations in quantum physics and quantum field theory, you actually rotate time to the imaginary direction, which is called the Euclidean time. And that way you can treat the time and space literally on an equal footing at the end of the day. And you might have heard of this idea that Stephen Hawking talked about imaginary time, and that's the origin of the imaginary time in quantum field theory. So you are right. The Fourier transform can be replaced by Laplace transform because of this I epsilon allows you to rotate the time axis on a complex plane from the real time to imaginary time. So often we end up computing things using the imaginary time integral instead of real time integral, because that gives you the same answer mathematically. But this imaginary time turns out to be useful too. And in addition of being useful in just performing integral, because now you have an exponentially converging integral rather than an exponentially oscillating integral, you can also use this as a way of computing the partition function in statistical mechanics using quantum field theory, because it turns out that the temperature is placing the periodic boundary condition in imaginary time direction. So this is, completely off the track from the discussion we are doing right now, but you're right. Rotating the axis from the real time to imaginary time to deal with the Laplace transform instead of Fourier transform is first useful mathematical trick, and second, that would allow you to deal with the finite temperature, and third, it appears in this imaginary time formulation of the quantum field theory. So it actually has many benefits of talking about it. But this is just the advertisement at this stage.
Okay.
Okay.
Thank you.
Any other questions? Okay, I see one chat. It says, thank you. Okay, you're welcome. All right, so let me finish this up. And as I announced that before the break, I will be back on Friday to teach in class. So I see you on Friday. And tomorrow, the section will be taught by email. And he will be talking about the Casimir effect, namely that if you look at the 0-point energy of the harmonic oscillator for the electromagnetic field, we normally drop the 0-point energy because we are not interested in it. But if you change the boundary condition of the 0-point energy by placing a parallel conducting plates, it turns out that you can measure 0-point energy, or rather the change of it. So 0-point energy actually affecting physics. So that's what we're going to hear from Emil tomorrow in discussion section. So I hope you wouldn't miss it. Okay, so bye for now.
Bye. Thank you.
Bye.